Hi, this is Professor Fernandez, and this is video 1A in lesson 19. So the A here refers to the fact that we are going to talk about the same topic, use substitution as an integration technique, across multiple videos. So this is the first of those videos. So I'll start here in this video by looking through two examples, 5.20 and 5.21 from Calculus Simplified. And first thing I'm going to say is you'll see that this first one is about an indefinite integral. This second one is about a definite integral. So I encourage you to review the definite and indefinite integrals content. So see videos 18.1 through 18.2 in this series for a review of that. In particular, for this one down here, we will of course be using the evaluation theorem. So let's get started then and take a look at the first example over here. This one says calculate this indefinite integral. Okay, so because this is a video about the use substitution technique, right? We know that we're going to use substitution. I'll talk later on at the end of the video how you might know to try that for this integral if you weren't given information that, this is where we're heading for this example. But for now, we're going to use substitution. So what does that mean? That means that we need to find a u in the integrand, here's the integrand, whose derivative is also in the integrand in some form. Okay, a lot of times, this is the use substitution technique is useful for integrating composite functions. So this is the place to look right here to see if we can extract that u, x squared plus 1 to the 100. So that's a composite function, and the inside function of that is x squared plus 1. The outside function is, x to the 100. So the fact that we have an inner function already tells us that that should be a good first guess for u. So this is one of the shortcuts, if you will, that I suggest for guessing what u is. You can try it. If it doesn't work, then you can go back and try a different u. But the shortcut is identify a composite problem, a composite function in the integrand, find the inner function, and then try that as your u. This is a shortcut that will work, most of the time, but not all of the time. That's kind of the point of these other videos in this lesson, to show you how use substitution can get a bit more complicated and give you some other techniques and shortcuts for those situations. Okay, so let's follow through here. If u is x squared plus 1, what is du dx? This is the derivative of u with respect to x in Leibniz notation. So that's just 2x. Depending on how you are used to thinking about what this implies, right? You can write this as the differential du is 2x times the differential dx. Okay, if you haven't discussed differentials yet, there's a short discussion of it in Calculus Simplified up here, what we're using for this course. But also, you might have seen this use substitution technique done straight from, if this is your u, just calculate the differential. Long story short, we know that dy dx is the derivative f prime of x for a function y equals f of x. So we define the differential dy to just be the derivative times dx. So that's what we're using here. The differential of u, which is this function, is the derivative of this function, which is 2x, multiplied by dx. Okay, so with all that being said, you can see why in differential form, it's a little more natural to use that form to make progress on integration by use substitution. Because we now look in the integrand and we try to find where u and du appear. And you can see, of course, that that was our u, and 2x dx, that is over here. All right. So again, because this is a first example, everything fits very nicely. And so what's going to happen once we substitute these things in there is you'll see that we will immediately have all the x's go away. So this is going to be the integral of, the blue stuff here becomes just du, right? 2x dx, 2x dx, that's literally du. And then this we keep saying here is u, so this becomes u to the 100. So you can see right away, like I said, that there are no x's remaining. And this is really when you know that you have accomplished the first step in the use substitution technique, which is to convert your integral in terms of x's, usually, and not some of the variable t's or whatever, to an integral that does not have that variable anymore. The second step of whether you know that this is going to be a useful technique, u-substitution, to employ in an example, is whether doing this process actually simplify the integral. Okay, so let's answer that question right here. Right, if we go back, we will need that u was x squared plus 1 later. If we go back and we just kind of look at this integral, this is not something we knew how to do before now. So that was another reason to maybe try an integration technique. We have now, via our substitution over here, re-expressed the integral as this. And this is really just u to the 100. We know how to integrate that. That's the integral version of the power rule. We add 1 to the exponent, divide by the result, and it's an indefinite integral, so we add plus c. Okay, many people think, okay, I'm done. The answer is u to the 101 divided by 101 plus c. The problem, of course, is that the problem initially had x's, and now here we are in an answer that has no x's, right? So we have to go back to x world. And the way we do that is by going back to our substitution. So u was x squared plus 1. So the last step in the problem, one more step, is to re-express this in terms of x's. So x squared plus 1 to the 101 divided by 101 plus c. So this is our answer now. The original statement of the problem was in terms of x. Our solution is in terms of x. So we've finished answering the question. It would be a good idea, right, just also to review some of your differentiation rules to ensure that this really is, in fact, the integral. How do you do that? Well, so take the derivative of this function, and you should get back the integrand that is up here. So let's take the derivative here. So this is a composite function. The 1 over 101 goes off for the ride. And then we differentiate x squared plus 1 to the 101. So we bring down 101, x squared plus 1 to the 100, right? That's the derivative of the outside. And then we multiply by the derivative of the inside. So I'm using here the chain rule. You can see that the 101s go away. And what you're left with is 2x, x squared plus 1 to the 100. That matches exactly the integrand that we started off with. Okay, so indeed we did the u substitution correctly, right? By which I mean we found a u that enabled us to convert the integral into something that did not involve x's and which we could do using some other integration technique. So that's what I mean by doing the u substitution correctly. And then also we, in fact found the integral of the original integrand. We know that we did that correctly because we checked our work. We differentiated our answer and we got back to the integrand. Okay, so I'm going to remove all this clutter now so we can go off and do the second example. And I'll, usually I do this, we'll speed things up a little bit for the second example now that we know how this works. Okay, so zooming in here, we're looking again for any, the simplest way to do this integral. This does not seem to be one of the integrands that we have studied. This is not like x to the fourth or some power function or, a difference of power functions or sum or something. So again, if you didn't know to do u substitution, this is a next logical step to try. And so there we are. So then the same guiding principle from before. Let's look at the integrand and see if we can pick out a composite function and then try u as the inner function of that composite function. Certainly there is a composite function here, and that is this part. And then the inner function of this composite function is x squared plus 4. So let's try that as our u. u equals x squared plus 4. Okay, so the differential du, again, is just the derivative, 2x times dx. Okay, and then we start substituting these two pieces in. Notice that unlike in the original first problem we did, there isn't quite a 2x dx in here. There's an x dx. All right. So one thing you can do to help you out with this, finding the du and the integrand, so you can go over here and it is an equation, right? So you can treat this algebraically like you would any other equation. Here is x dx, it's multiplied by 2. So why don't I divide by 2 on both sides? And I isolate my x dx. And then I can say, oh, okay, Great. So going back to my integrand, x dx, this part right here, is literally 1/2 du. So this is going to be integral of 1/2 du. And then over here, I have x squared plus 4 to the third. So x squared plus 4 was my u, and I'm raising it to the third. So this is u cubed to u. All right. I will mention a couple of things here. So notice that I've written an indefinite integral. Why have I done that? Well, here's the thing, right? If I kept the same numbers, 0 to 2, what would I be saying? I would be saying that these two integrals are equal. And that would mean that, u equals 0 is the same as x equals 0. But that's not true, because if we look at our original substitution up here, right, when u is 0, x is not defined. X squared plus 4 is never 0. So that's kind of math telling you that there's something going wrong here if I add the 0 here, and also you'll figure out that the 2 is not, when u is 2, x is not 2 either. So there are two options to treat this issue. The one that I recommend is what I'm doing here. Ignore the limits of integration and instead focus on finding the antiderivative of the integrand. Right? Remember how this works when I'm doing a definite integral. Right? If I'm integrating from a to b little f of x dx, the evaluation theorem says the first thing I do is to find an antiderivative, capital F. And what is capital F? Capital F is the indefinite integral of little f. Okay? And then the evaluation theorem says you evaluate that from a to b. So in other words, as the evaluation theorem tells us, it's a two-step process. First, find the antiderivative, and then, second step, evaluate f of b, capital F of b, and capital F of a, and subtract. So this is the same, step-by-step process that I recommend you do in u-substitution. That way you don't get confused and inadvertently assume that these limits of integration go through, because in many cases, I would say maybe even most cases, they are not the same limits of integration. At the end of this calculation, I'll show you how you could do this as a definite integral and how you would, in fact, find the correct limits that should belong here. Okay, but I'm going to keep going here and do this as I have suggested. So we're just going to find the indefinite integral of this integrand first. That's what we're doing here. So I'm not going to put equals because they're not equal. And then we'll go back and use that in the evaluation theorem. All right, so integral of u cubed du. This is another instance of the integral version of the power rule. I'm going to add 1 to the exponent, divide by the result, and then there's a plus c here. You might be wondering, why don't I put this in brackets? And, more information, right? If I did, and I distributed the 1/2 u to the 4th over 4 plus 1/2 c, remember c is an arbitrary constant. So you multiply a number that you don't have a fixed value for times 1/2, you get some other number you don't have a fixed value for. So we could call this arbitrary constant d, u to the 4th over 4 plus d. And then, not much has changed, right? So to, save us some of that work, I just go off and write what I originally wrote. Okay, so then this is the indefinite integral of this integrand. But again, like in the earlier example, it's in terms of u. So I need to go back and express it in terms of x using my original substitution. So this is x squared plus 4 to the 4th divided by 4 plus c. Great. So as we said earlier, we have now found capital F of x in terms of what the evaluation theorem says. If this is the integrand, little f of x, then we have now found its antiderivative, capital F of x. So in terms of the evaluation theorem, we can now write an equation, right? We can say this integral, definite integral here, equals the capital F of x function, in other words, the antiderivative, x squared plus 4 to the 4th over 4, and then evaluated from the same limits of integration, right? 0 to 2. Okay, at this point, if I erase everything we did down here with the u-substitution process, right? This is a true statement, right? And this is something you might see, as a question on a quiz or something. In other words, this really is the antiderivative of this function. And again, we can check that. So how would we check that? Like we did before, we would differentiate capital F and verify that it equals the antiderivative little f of x. I won't do that here, but I'll leave that for you to check. And then now all that's left to do is to do the evaluation theorem step. So take this number 2 and substitute it in for x, and that's going to give you 1/2, let's see, 1/2, 2 squared is 4 plus 4 to the 4th over 4, and then subtract, take this number 0, substitute it in for x. That'll leave you with 1/2 0 squared plus 4 squared, so just 4 squared divided by 4. Okay, and then you do the arithmetic here, and then that will be your answer for the definite integral, ends up being 480. All right, so now let me go back and show you what I said originally, which is how you might do this differently, right? So how do I actually put in the limits of integration with the in the u-substitution step? So if you remember, we had written this integrand, this indefinite integral. We had expressed this as 1/2 u cubed du. And the conversion here was u is x squared plus 4. Okay, to actually write this now as a definite integral, here's what we can do. We can say this equals 1/2 integral of u cubed du, and now we have to figure out those limits of integration. And the way I'm going to do that is I'm going to use my conversion between u and x. And I'm going to say, look, here on the left-hand side, when x is 0, right? If I go down here, if I plug in 0 for x, u is 4. So the u lower limit of integration corresponding to x equals 0 is 4. So I'm going to put the 4 over there. This is how you convert the limits of integration. Let's do it again. So when x is 2, I'm going to go back down to my conversion here, and when x is 2, this becomes 2 squared, so that's 4 plus 4, that's 8. So u is 8. I'm going to take that and put it in as my upper limit of integration. So if I remove the clutter, then you can see that I have now achieved what I set out to achieve, at least for now, which is this is an equation of one definite integral in terms of one variable with another definite integral in terms of a different variable. And of course you can see that this helps us because before we had no idea how to do this, and now this is again just integral version of the power rule. You would integrate this as normal. You'd say 1/2 u to the 4th over 4, evaluated from 4 to 8, right? So the nice thing here is that you do not need to go back and substitute in x squared plus 4 for u. Why? Because this whole thing is a definite integral with limits in terms of u. So now here you would just do the usual evaluation theorem step, right? Plug in 8 for u, 8 to the 4th over 4, minus plug in 4 for u, 4 to the 4th over 4, subtract, and then you'll end up getting the same 480 that we got before. So either way you do a definite integral using u-substitution, whether it's the first thing we did, or you just focus on the indefinite integral first, convert back to x's, and then keep the original limits of integration. Or this is method number 2, where you convert the limits of integration and then stay in u land the whole time. You will get the same answer. All right, so I'll zoom out here and then mention one very quick thing. As I said earlier, how would you know to use u-substitution if you weren't told, as the title here suggests, right, that this is a time when you need to use it? Again, that goes back to something I've alluded to and used throughout the video. So look for integrands that have composite functions in them. X squared plus 1 to the 100, composite function. The inner function, x squared plus 1, great thing to try for you. X squared plus 4 to the 3rd, composite function. The inner function, x squared plus 4, great thing to try for you. And in both of these cases, right, those particular choices of u worked out beautifully and were enabled us to actually solve the integrals. Great, thanks for watching.